Okay. Okay, I welcome you all intellectual adventurers in this meeting. So today I'll talk about numerical methods for the nonlinear systems. So currently I'm teaching this course at IIT Mandi as a part. So this lecture is a part of computational methods for physicists, which I'm teaching at IIT Mandi. So let's get started. So first, let me talk about introduction and motivation. That why should you be interested in studying about nonlinear solving methods for nonlinear systems, the numerical methods, I mean. So maybe some of you, at least those of you who are from physics or chemistry background, maybe know this about the van der Waals equation of state. So first thing is, so before talking about that, let me state it that nonlinear equations are also very ubiquitous in physics. So some examples. So first example I'm taking here is the van der Waals equation of state. So here, if you must recall that the ideal gas equation is PV equals nRT, which is true when you consider finite that the gas molecule is infinitesimal size and there is no mutual attraction between gas molecules. But when you consider this aspect, that you consider that the gas molecule size is finite and also there is mutual attraction between the gas molecules, then this equation takes this form. Okay, so when you take A and B to be 0, then you get back this. So now if you assume that you know the pressure, the temperature A and B, how do you calculate the volume? So in that case, you will get a cubic equation. Okay, so in general, so although we know that how to solve a general cubic equation, but then it will serve a method, or rather it is a specific case of all the equations that we can solve using nonlinear methods. So maybe you also know about the Abel-Ruffini theorem that says that for a general polynomial equation of degree 5 or more having arbitrary coefficient, there is no solution in radicals. So radicals means that you can use square root as many as you want. You can take as many cube roots, fourth roots, fifth roots, etc. So if you have any polynomial that has degree 5 or larger than 5, then in general it is not possible, though it is possible for all polynomials of degree 4 and less. Okay, so the next example that I'm taking from quantum mechanics is the example of finite potential well. So in this case we solve this differential equation. Okay, so this is second order linear differential equation, and where V is given by this. So as you know that solving the equation leads to states of odd and even parities. That's not very important right now, but the important part is that you get this sort of equation, because as you know that in the quantum mechanical system, all energy states are not allowed. Only the system can only take some discrete energy states. Okay, so the same thing happens here. So in order to calculate the energy states, this is the equation you need to solve. Here k, kappa and this k are related to here kappa and k are related to the potential v0 and the energy. Okay, so if you solve this equation, you will get the allowed energy states. Just a second. Okay, so I can write this equation in this form, that in the form of an equation. So if you just take it to this side, then you're solving k tan ka equals minus kappa equal to 0, of course, which is the same as this equation, the one we wrote before. So in this equation we will, so in this course, or rather in this lecture, we will deal with solving equations of the type fx equal to 0, where fx can be any nonlinear function of x. Okay, it can be any sort of nonlinear function. So of course you can use some clever methods that whether the solution exists or not, but that's a different story. But if you want to solve the equation and get its root, then these methods that we're going to discuss would be helpful. So one more example. So since we recently had launched the Aditya L1 satellite, so this example will also be contextual. So as we all know that Aditya L1 has gone into the space to reach the Lagrange point L1. So Lagrange point L1 is after the French mathematician Joseph Louis Lagrange. So Lagrange points are equilibrium points for small massive objects under the gravitational interaction, because in this case you have sun, earth, and satellite system. So it's a three-body problem. So it turns out that there are 5 such points, and these are the excellent location points for satellites, as the fuel requirements are minimum. So in order to get the value or the distance of the Lagrange point from Earth, because we are calculating L1, okay, so L1 is one such Lagrange point, and then you get the value of L1 by solving this equation. So this fifth degree equation, by solving this fifth degree equation, you can get the location of the Lagrange point from here. So this is the value. So this is the equation we are solving for in terms of x, which is r over r. So r is the distance. So this is the Lagrange point, and you are comparing it with the distance between sun and the earth. Okay. So here also you will use nonlinear equations. Okay, so now let me turn to the problem statement. So we have to find out, so given a function fx, we have to find out all x star such that f of x star is equal to 0. So these x star, as we all know, are called the roots of the function. So the function fx can be anything. So as I said, the function fx can be anything. So in particular, the function can be a polynomial function. For example, this c0, c1x, and cnx power n. So one example would be the Legendre polynomials, which are very common when you study physics. They can be other function also, like Chebyshev, Bessel, etc. And it can be even some complicated function like this. So here, this function depends upon L and X. So for a particular value of L, this is an integral, and then you can again find it's 0. But then this is not pretty straightforward, because you have to evaluate an integral in order to evaluate the function itself, as X comes here. So complications will arise in case of polynomials, as they will have multiple zeros. And we can go to the next level of difficulty, which is when you solve a system of nonlinear equations. So once we get hold of just one nonlinear equation, we can then switch our gears, and then we can go to the next level of difficulty and can solve the system of nonlinear equations. Okay. So now let me talk about the summary of methods. So for the concreteness, I will adopt this example also. So I will use this example over and over again. So we will discuss about the fixed point iteration method and some other methods, as you will see. So one obvious thing can be to just make a plot. So here I'm plotting this function fx equal to exponential x minus the square root of x minus x, like this. So as you can see that since this function cuts the x-axis at these 2 points, so you have found the location of the roots. But then the problem is it's not a very good strategy, because many a times, so here in this case, of course, the function evaluation is very easy. So that's why you can get the roots very easily just by plotting the plot, or rather plotting the function. But the function evaluation can be very expensive, as we saw in the previous case, when you have to evaluate an integral all the time for just one value of x. So in those cases, it's not a very good strategy. And also, if you want to, so it may say that it's near about 1, but then what is the meaning of near about 1? You have to know whether it's 1.0001 or maybe 0.9996. So then you have to make even finer and finer and finer grade, and that's all visual. So in that sense, it's not a very good strategy, because and one more thing is, for multi-dimensional system, this is not this is very difficult to implement. Okay. So now let me give a brief summary of all the methods that we are going to discuss. So so we divide our root finding algorithms into 2 large classes. So one is the bracketing method. So here we start with 2 values of x, let's say x0 and x1. So we are sort of sure that the value of the root of the function lies between the interval x0 and x1. So that in that sense, it is bracketing, because we know the interval in which the root of the function will lie. Okay, so then we actually choose these values in such a manner that fx0 times fx1 is less than 0. The multiplication of these two is less than 0 at the for the function values. So then, by the Bolzano's theorem, there exists x star in this open interval or in other words, there will exist a root between this, at least one root between x0 and x1 by Bolzano's theorem. So one example is bisection method, as we will see next. The other one is non-bracketing method. So these are known as the open domain method. So here you will start with just one guess, some guess that you think is close enough to the actual solution. Okay. So, but the difference is that it does not require a range to be specified. So the methods that we will talk about in this lecture would be fixed point iteration and Newton Raphson method. Okay. So before getting into the methods themselves, so it would be useful to understand the convergence order and criterion. So like how do these methods converge? How fast do these methods converge? Okay. So while talking about the root finding algorithms, because these will be approximate only, so we will again resort to iterative methods. So what do I mean by that? So you first make a guess and then you just keep improvising it. You will make it better and better over the time, over the iterations. So as I said, that you are not actually computing extra because that's not possible. That's why you're using the method in the first place. So then it happens like this: x0, x1. So it is assumed, or it is you're hopeful that the method will converge to the, or will go towards the root of the function that you're looking at. So you say that the sequence is said to have the pth order convergence if you have some number m which is greater than 0 and a number p such that this condition is satisfied. So you say that this sequence has a pth order convergence. So this is the mathematical definition. So here m is known as the asymptotic error constant. So some specific cases, so when you take p equal to 1, you will get linear convergence. So this kind of thing happens when you consider fixed point method, which I will discuss next, and the bisection method. And when you take p equal to 2, you will get quadratic convergence. So this happens with the Newton Raphson's method. So in that sense, Newton Raphson's method is converging fast as compared to the fixed point method or bisection method. Okay. So, but you also need to put the stopping condition. So of course you will keep improvising this sequence or the estimate of the actual root, but then you must also specify the computer that when should the computer stop. Okay. So maybe you can use this stopping criterion. So xk is the value of the root at the kth iteration, and this is the k-1 iteration, and then you can make it as accurate as you want. So you can choose epsilon to be, let's say, 10 to the minus 6. So depending upon the epsilon you choose, you will get that much amount of accuracy. Okay. So now let's first talk about the fixed point iteration. So fixed point iteration solves the problem of finding x such that x equal to gx. So instead of directly calculating the root, so it first calculates the fixed point of a given function, but then that can be used to calculate the roots of a function. So as I will explain. So first let me say what is the meaning of a fixed point. So I'd say that x star, a real number x star, is called a fixed point if it satisfies this equation, x equal to gx. So this is the fixed point of the function gx. Okay. So for example, the function gx equals x square minus 6 has its fixed point at 3 and 2. So because these are the solutions to the quadratic equation, x square minus 6 equals x. Okay. And this function has no roots because x can never be equal to x plus 2. Because that would mean 2 is equal to 0, and that is not possible. Okay, so then the equation x equal to gx gives us a hint to use the following iteration. So then you start with an initial guess like x0, and then you evaluate this function at x0, so that becomes your next iterate. And then you evaluate and then you plug it in back here, then you get the next iterate, and you just keep improvising it. So I'll show you an animation. So until you get sufficient convergence, you will just keep improvising it. So thus you can write that xk is equal to x g gxk minus 1. So let me show you how it is done. So let's say, so these are various number of iterations. So you start with x0 and then you substitute it in here. So that's your first iteration, and then you will get a new value of x. So that becomes your second iteration. So that becomes your g here x for gx at the second iteration, and so this is now an improved estimate of the root, and then you again plug it in back, and then you get the more even hopefully even better approximation for the root, and then you will just keep improvising it until you get sufficient convergence. Okay, so this is what you do. So let me now give an example of the fixed point iteration. So consider this function as an example. So fx equals exponential x minus square root of x minus x. So in this case, it is easy. So if you take function gx, so you're actually finding the fixed points of gx. So now finding the fixed points of gx is the same as finding the roots of the function fx, as you can see here. So if you make a plot, so this is your line. So geometrically, what does it mean to calculate the fixed points? That it is the intersection point of the line y equal to x with the function you're looking at. So then if you make the plot of y equal to x, which is this orange line, and y equal to exponential x minus square root of x, which is this this blue line, as you can see that you get the same roots as you must get, because these are the points at which fx cuts the x-axis. So the two must be the same. Okay, so now let's start with an initial guess. Okay, so let's say you start with an initial, because remind you, this is the open interval, or in this case you will not have two values to start with, or you will rather start with an initial guess. Okay, so this is different from the bisection method that we'll also discuss. So let's say you start with some point between 1 and 2.5, and then you will use that algorithm, and then you can see that it is approaching towards this value. Okay, that it is approaching toward 1. So if you just keep improvising it, like x equals gx, so xk minus 1 equals gxk minus 2. So we'll just keep improvising it, and then you are able to see that it is converging towards 1. Now what happens when you take x initial guess to be greater than 2.5? So this is what is happening, but in this case it is not converging. So though there are two roots, the solution is not converging to this point. It is only, if at all it is converging, it is converging to this point, as you will see next. So the third possibility is it is less than 1. So now what happens? It is again converging to that point. So now we should pause and ponder about what is actually happening. So if at all the sequence xk is converging, it is converging to x equal to 1. It is not converging to the second root, because the function also had the second root that it has 2.5, about around 2.5. Otherwise it is diverging. So depending upon the initial guess, either it is converging or it is diverging. But if it is converging, it is always converging to x equal to 1. Okay, so we can also take logs on both sides, because so this equation, if you take a logs on both sides, of course, assuming that none of these quantities are negative, so then you can take the log, and then you get this, and now you can again start looking at the fixed point of this function, ln x plus the square root of x. Instead of looking for the fixed points of e to the power of x minus the square root of x, you are now looking at the fixed points of ln x plus the square root of x. And let's see what happens, because this is the same as before. Just by taking log or sine of both sides, the roots will not change. They will remain the same. Okay, so this is what I said. Now if you take this, so now since you are locating the fixed points of ln x plus the square root of x, so this is how the function looks like, and this is the line y equal to x. Okay, now let's see what happens. So here in this case, now let's start with an initial guess that lies between 1 and 2.5. So here you can see, although it is very slow, but it is approaching towards 2.5 now. Now it is not going towards 1. As you can check by plugging in the values, it is If at all it is approaching, if at all it is converging towards 2.5. Okay. So now you may take the next guess at to be less than 1. So let's see now what happens. So it is now diverging away. It is moving away from the root. Okay. Now the third case is when this is greater than 2.5. So in that case also you can see that it is converging towards the other root 2.5. Okay. So this is different from before. Initially it was converging to 1. Now it is converging to 2.5. So let's have some more reflections about the fixed point iteration. So recall that if we were taking gx to be x e to the power x minus the square root of x, then the method was converging to x equal to 1. But it was not giving us the other root, which was approximately 2.5. So now instead we take gx to be ln x plus square root of x. The method was converging to x equal to 2.5. Okay. So does it seem that fixed point method is not a very robust method because you were not able to really locate the other root as well? And it depends upon the form you choose for that. So when you choose some form, it will converge to one root. If you choose some other form, it will converge to some other root. So we need to work better. So before that, we explore the convergence properties of the method to understand it better. So it turns out, as we said before, that it exhibits the first order convergence. So another first order convergence method is the bracketing method. So now we talk about the bisection method. So bisection method is you've already bracketed out the root, that you know the location of the root. Okay, so the root lies between, let's say, A to B. Okay, and then you use the Bolzano's theorem. Okay, so Bolzano's theorem says that let f be a continuous function for x in A and B, and f of A times f of B is less than 0, then there exists at least one x star in A and B, such that f of x star is equal to 0. So this is what the Bolzano theorem says, and this is what we're going to use. So the idea is to use Bolzano's theorem repeatedly, and so you start with some initial guess, and you just keep halving the interval, and you just keep using Bolzano's theorem. So the steps are the following. So first is you have taken the interval a comma b. You take the midpoint of a and b, that is x0, which is a plus b over 2. And so if f of x is f of x0 times f of a is less than 0, then you replace a by a. I mean, you don't change a, but you change b to x0. Otherwise, you do some other thing. Okay, so it will be clear from this animation. So, and you repeat this, and you repeat the steps unless you reach sufficient tolerance. Okay, so this is how it is done. So let's say you have these 2 points a and b, between which you know that there exists at least one root because of this condition. So then you take the midpoint of a and b, which is x0. So that's your iteration 1, but it won't be a very good estimate. So now we will go to iteration 2. So what would you do? So you check whether f of a times f of x0 is less than 0. So if that is the case, then you halve the interval. So your new a and b will become like this. So your new b will become like this, and then you will leave b, and then you will leave out b. But if it is not the case, oh yes, and then you will get a new estimate of the root as the midpoint of a new a and b. Okay, but if f of a times f of x0 times f of b is less than 0 instead, not this but this is true, then you do different thing. So then your new a becomes x0 and b remains the same, and then again the new estimate is the midpoint of a and b. So, and you just keep doing it again and again, because out of these two conditions only one will be true. So let's say if this is true, then you just discard this part and you just keep halving it. And so in that way you will just improvising over the root until you get sufficient convergence. So that's your iteration 2. So now let's see how it is. Now see an example of the bisection method through an animation. So let's say you started with a and b like this. So we know that our root is at 2.5. Okay. So now you will half the interval. So the midpoint is about this x0. So now you can see that in this case the product this and this is positive, but the product this and this is negative. So you will just get rid of a and will now change your now change your midpoint. So this x1 is your next estimation of the root, and now you will discard b because the product of this, the function value at this and this is negative. So you will get rid of b, and then you will again half it, and then you will just keep doing it. So as you can see, you are approaching more and more towards the root in this way. Okay, so you will keep doing it and until you reach sufficient convergence. So this is your third estimate, and then you will get rid of this, and then you take a midpoint between x3 and x1, and so on. You will just keep repeating it. Now, one of the methods is the Newton's method. So Newton method, as we talked about before, exhibits second order convergence. It converges very fast, or we also call it as Newton Cotes method. Okay, I'm sorry, Newton Raphson method for evaluating the roots. So one advantage is that it is easy to generalize to high dimensions, and the same thing happens with the fixed point iteration method as well. So just one difference here is that we also need to know the value of the derivative. We need to know the function value and also the derivative at a given point. Then you can use it. So this method won't be helpful or won't be useful in those cases in which the function evaluation is very costly. Okay. So and just like and it's also the non-bracketing method. So you have to start with an initial guess that so if you're very close to the root in your first guess, then you will very quickly converge to that solution. But if you are not, then it may take some time. Okay, so it has quadratic convergence, but it has also some possible caveats. Okay, so algorithm. So this is again going to be an iterative process, just like the bisection method and the fixed point iteration method. So we assume that the function you are trying to calculate the roots of has first and second order continuous derivatives. So let's say xk minus 1 is the latest iterate. So Newton's method gives the next iterate in this way. And how do you understand, or how do you understand this result? So let me explain it a bit. Okay, so before going into that, let me explain you the geometrical meaning. So first you start with an initial guess like x0, and then you draw a tangent point at x0 and fx0. I mean at this point, and wherever it cuts the x-axis, that becomes your new guess. Okay, and then you will just keep improvising it. So I'll give an example through this thing. So I'm again taking that example of exponential x minus the square root of x minus x, fx equals exponential of x minus the square root of x minus x. So let's see what happens in this case. So let me zoom it a bit for you in order to just look at the only one of the roots. Okay, so you start with some point. So this is your x0, and then then you draw a tangent at point x0 and fx0. So this is what you get. So this is your new estimate of the root of the function, and then you again draw tangent at x1 fx1 and like this. So this becomes a new estimate, and you just keep repeating it. So as you can see, it is approaching very fast to this root. Okay, so this is how it works. So as I said that the pth order convergence for the sequence is defined in this way. So Newton's method exhibits second order convergence. Okay, so now there can be possible caveats with Newton's method. So one can be, in some cases it can have slow convergence where the derivative value is very small, because that will eventually come in the denominator. So the solution may blow up. Okay, and it can also get into an infinite loop like this. So for example, for this very symmetrical function, you start with some point over here, and then you so let's say here as the root of as the root, and then you draw tangent at x0 fx0. It will reach you, it will make you reach there, and then you will again reach there, reach here, reach here, reach here. So you will just, so you will be in infinite loop. You will not really converge to the root of the function. So, and it can also be problematic in case of multiple roots. So in okay, so thank you for your attention. For the time being, I'll talk about only this, and the remaining part of the lecture will be covered in the next class. Thank you. तुम्हारी आवाज रिकॉर्ड कर रही है।